Hello everyone. In this lecture, I want to introduce a very interesting application of optimization analysis. It is called the network modeling theory. It's a very useful tool to address some practical questions we meet every day. In this lecture, I want to introduce this theory to you. Before today's lecture, let's take a look at Google Map. I believe most of the class have been using Google Map a lot on a daily basis. It is very important to travelers, internet users, and businesses. Suppose I want to travel from the university, Texas A&M University Commerce, to the DFW International Airport. I want to find the route that I need to spend the shortest time. Then I can search Google Map. First, I click the direction button, and then in the starting point, I type in Texas A&M University Commerce. Find the starting point. And then in the destination, I want to type in DFW International Airport. After that, Google Map will give you three options. The one in blue shows you the route that needs the shortest time. As you can see on the left panel, it just needs about 1 hour and 17 minutes. The other two options you can choose, but it will take you longer time. For instance, the one going through Plano will take 1 hour 22 minutes. The one going through McKinney will take you 1 hour and 26 minutes. It's very useful to use Google Map, but I'm not sure. Have you wondered how Google Map finds the shortest route for us? Suppose we only have one option, the one as you can see in blue. We have to go to Rockwall and then go to the DFW. Suppose we only have this route. It's easier to calculate the time that is needed for traveling, right? What we can do is we calculate the time between two cities. Let's say Commerce and Greenville, Greenville and Rockwall, Rockwall and the DFW Airport. Then we add this time together. That will be the total time that is needed between Commerce and DFW Airport. But since we'll get a little complicated if we can have multiple options. In this case, we could go through Plano, we could go through McKinney. How can Google find the shortest time for traveling? Obviously, Google cannot hire thousands of people to calculate the best solution for the map users. It will be better if we can develop an algorithm or a program to find the shortest route, best solution for the travelers. We use network modeling to address this issue. This is what we will talk about in this lecture, the network modeling theory. This analysis technique is frequently used in finding the shortest route, the route that needs the least amount of time, and so on. I want to use an example to show everyone how to use network modeling to find the route that needs the shortest amount of time for the travelers. A salesperson is in a hurry to drive from Birmingham, Alabama to Virginia Beach to meet a very important client. Because she wants to get there ASAP, she wants to find the route that needs the least amount of time from her. According to her knowledge and experience, she draws a map. In this map, she shows all the possible cities she could choose to reach Virginia Beach, and also she estimated the time between two cities. For instance, as you can see in this map, between Birmingham and Chattanooga, she estimated that it will take about 3 hours. If she travels from Birmingham to Atlanta, it takes about 2.5 hours. And then she used the same technique to find the the subsequent paths she could use. This consists of the map, as you can see on this slide. In order to simplify the analysis process, we give each city, instead of using the city name, we give each city an ID number. We use ID number 1 to represent Birmingham, Alabama. We use ID number 2 to represent Atlanta, Georgia. We use ID number 3 to represent the city of Chattanooga, and so on and so forth. Finally, for the destination city, Virginia Beach, we use ID number 11. At the beginning of this lecture, I told everyone that network modeling is an application of an optimization analysis. Before we talk about network modeling in greater details, let's use what we have learned in an optimization analysis to talk about this question. I told you that we need to go through 3 steps in an optimization analysis. First, identify the objective variable. Find the goal. Second, find the decision variables and then build the objective function. Third, we want to find the constraints in our analysis question. The last step is very important. We want to find the constraints. Let's use these steps to talk about this question. What is the objective variable? Since the salesperson wants to reach Virginia Beach ASAP, the traveling time should be minimum, right? So the shortest traveling time should be the objective variable in our analysis. The next question is, how can we reach the minimum traveling time? In this map, she already estimated the time between 2 cities. If we can find out which path we'll be using for the driver, that will be good. We just add the time together. That will be the total time. Let's say I choose the right one. I want to travel from Birmingham to Atlanta, Atlanta to Greenville, and so on and so forth. And then I just add the time on each path together. But the question is, which path should be chosen, right? When we make decisions as a human being, we would say, yes, I want to travel from Birmingham to Atlanta, but not to Chattanooga. Or you can say, yes, I want to travel from Birmingham to Chattanooga, but not to Atlanta. This is what we, human beings, say. If we can translate this human decision into a mathematical way, that will be great. The computer software is able to understand this decision as well, right? How about this? Let's create the variables for each path. Let's say if we want to choose the path between Birmingham and Atlanta, we create a variable called x sub 12. As you can see here, x sub 12. This indicates the path between Birmingham and Atlanta. And then we want to give value 1 to x sub 12. This indicates that we want to travel from Birmingham to Atlanta. We can also do the same for the path between Birmingham and Chattanooga. Let's create a variable called x sub 13. As you can see here, x sub 13. And then we want to give value 0 to x sub 13. That means we do not want to travel from Birmingham to Chattanooga. By doing this, I can translate the first possible human decision into a mathematical way. As you can see, the 2 equations at the beginning are as same as the human decision, the first human decision you can see here. We can also translate the second human decision into the second 2 equations. Let's say I want to use the route between Birmingham and Chattanooga, but not Atlanta. Then I can give value 0 to x sub 12. That means I don't want to use the route between Birmingham and Atlanta. I want to give value 1 to variable x sub 1, 3. I want to travel from Birmingham to Chattanooga. This is how we translate the second possible decision into the equations here, as you can see here. Since every path in the map has a possibility of being chosen, and also we already know the time on each path. So when we build the objective function, we should use the time to multiply the variable for each path. As you can see here, 2.5 times x sub 1, 2 plus 3 times x sub 1, 3 and so on and so forth. We need to use the time on each path to multiply the variable for each path. We need to do this for every path in this map, and then add them together. That will be the objective function we are interested. Our goal is to minimize the value for this equation. That will be the shortest travel time. Some classmates may have a question. Professor, if I add all these paths into one equation, the time will be very large, right? Now think about this. Because between two paths or between several paths, we want some paths to be 0. We want the value of some variables to be 0. Let's say we choose Atlanta but not Chattanooga. Then x sub 1, 3 will be 0. 3 times 0 still is a 0. It will not influence the total traveling time. We identified the objective variable, decision variables, and the objective function. Next, we want to identify the constraints in our analysis. Some classmates may say, the constraint should be shortest travel time, right? No. Shortest travel time is the objective variable. It's the goal we want to reach. What should be the constraint then? Let's start with Birmingham. I have two possible paths, either going to Atlanta or going to Chattanooga. But think about this. No matter which path I choose from Birmingham, either Birmingham to Atlanta, Birmingham to Chattanooga, no matter which path I choose, the total value of x sub 1, 2 and x sub 1, 3 should be 1. If I choose from Birmingham to Atlanta, that means x sub 1, 2 equals to 1. Also, that means x sub 1, 3 between Birmingham and Chattanooga should be 0. 1 plus 0 is 1. If I choose from Birmingham to Chattanooga, x sub 1, 3 equals to 1. X sub 1, 2 should be 0. 1 plus 0 is still 1. This is the constraint we should consider. Use the same logic. Let's talk about the destination. No matter I reach Virginia Beach through Luxembourg or Raleigh, the total value of x sub 10, 11 and x sub 9, 11 should be 1. If I choose the route between Raleigh to Virginia Beach, x sub 10, 11 should be 1. And then x sub 9, 11 should be 0, right? 1 plus 0 is 1. If I travel from Luxembourg to Virginia Beach, then x sub 9, 11 should be 1. That means x sub 10, 11 should be 0. 1 plus 0 is still 1. If we present these two constraints in a mathematical way, you can see here the first constraint equation and the last constraint equation. No matter I travel from Birmingham to Atlanta or Chattanooga, the total of these two variables should be 1. Because Birmingham is the starting point, I want the total value to be -1 to indicate Birmingham is the starting point. Actually, because I have a negative number on both sides of the equation, finally, if you find the final equation of the first one, it's still x sub 1, 2 plus x sub 1, 3 equals to 1. I just want to use a negative on both sides of the equation of the equal sign to indicate Birmingham is the starting point. For the last equation, no matter I travel from Luxembourg or Raleigh to Virginia Beach, the total value of these two variables should be 1, because Virginia Beach is the destination. I want to use a positive 1 to indicate this equation. The first one and the last equation actually are the same. No matter which path we choose, the value of the total path should be 1. This is how we analyze the starting point and the ending point in a map. What about the points, the cities in between? They look a little more complicated than the starting point and the ending points. Let's use Atlanta as an example. Suppose the software finally chooses Atlanta as the next city we want to travel to. Then x sub 1, 2 should be 1, right? What about the next step from Atlanta? We can go to either Greenville or Chattanooga. We have 2 possible paths to choose from Atlanta, right? As we just discussed, no matter how many paths we have, the total value of all possible paths should be 1. That means x sub 2, 4 plus x sub 2, 3 equals to 1. We just said x sub 1, 2 equals to 1. That means Atlanta is chosen, right? 1 minus 1 should be 0. Or we can present the constraint in the second constraint equation, as you can see here. X sub 1, 2, that means Atlanta is chosen as the next city from Birmingham. And then from Atlanta, we could go to Greenville or Chattanooga. No matter which path we choose, the total value of these 2 possible paths should be 1. We said that x12 is already 1. 1 minus 1 equals to 0. And then you can see the second constraint equation like this one. X sub 1, 2 minus x sub 2, 3 minus x sub 2, 4 equals to 0. In this map, we need to consider all possible mid-cities. And for each mid-city, we need to build a constraint equation like the one we created for Atlanta. These are the constraint equations for our analysis. What is the key feature of this map? As you can see, our decision in the current step can strongly influence our decision in the next step. Let's say I choose from Birmingham to Atlanta. Then the next step is I have to choose a path from Atlanta to the next city, right? My current decision can strongly influence next decision, or the next decision is strongly dependent on my current decision. As you can see, decisions have a dependent relationship. If you have a question like this, we call this question a network. We call each point, each decision point in a network, like the cities you can see in this map. Each decision point a node. We call each dependent relationship in a network a path. In the future, if you see a question similar to this one, we call this question a network modeling decision. Now let's implement this analysis in the Excel software. Let's open an Excel spreadsheet, and then in C4, I want to type in starting city. In D4, I want to type in destination. And then in E4, I want to type in travel time. And then in F4, I want to type in chosen. These are the labels for different columns. Next, I want to transform the information listed on this map into the spreadsheet. I want to look at each possible path between 2 cities first, and then translate all the possible paths into Excel file. For instance, from city 1 to city 2, I need 2.5 hours. From city 1 to city 3, I need 3 hours. From city 2 to city 3, I need 1.7 hours, and so on and so forth. I have already printed off the map paper, so let me type in the number directly into the spreadsheet. City 1 to city 2, this is one possible path. I need 2.5 hours. City 1 to city 3, this is another possible path. I need 3 hours for this path. And then city 2 to city 3, I need 1.7 hours. And then from city 2 to city 4, I need 2.5 hours. And then from city 3 to city 5, between Chattanooga to Kerrville, I need 1.7 hours. And then from city 3 to city 6, I need 2.8 hours. Next, we need to look at city 4. From city 4, I can go to Charlotte or Asheville, number 6. City 4 to city 6, I need 2 hours. And then city 4 to city 7, I need 1.5 hours. Next, look at city 5. From city 5, I can travel to city 6, Asheville. I need 2 hours. 5 to 6, I need 2 hours. And then I can travel from city 5 to, let's say, city 9, Luxembourg. If I choose this path, I need to spend 5 hours on road. Next, I need to look at city 6. From city 6, I can go to Luxembourg. City 9, I need 4.7 hours. From city 6, I can go to city 8, Greenboro. City 8. If I choose this path, I need to spend 3 hours. Next, let's take a look at city 7. From city 7, I can go to city 8, Greenboro. I need to spend 1.5 hours. City 7 to Raleigh, number 10. I need to spend 2.3 hours. This is city 7. City 8, from city 8, I can go to city 9, Luxembourg. I need to spend 2 hours. City 8 to city 10. 1.1 hours. Next, city 9. From city 9, I can reach my destination, Virginia Beach, city 11. I need to spend 3.3 hours on this path. This is city 9. Next is city 10. From 10, I can reach my destination, Virginia Beach as well. If I choose this path, I need to spend 2.7 hours. You can save this file onto your computer. Let's take a look at the map. Totally, we have 11 cities and 18 paths. So let's count how many paths we have. We have 18 paths. This is correct. In the chosen column, we want to use chosen column as the decision variable. In order to highlight this range, I want to change the background color to light blue. This shows these are the decision variable. What should be the values in this range? They are 1 or 0, 0 or 1 to indicate which path will be chosen, right? Next, I want to find a cell to hold the objective variable. Let's use the C24. I want to type in total travel time. And then in cell D24, I want to calculate the total travel time. I want this value to be as small as possible. In order to highlight this is an objective cell, I want to change the background color to yellow. And then in D24, I want to type in equal sign, sum product. For the first range, I want to choose the decision variable from F5 to F22. And then a comma. I want to select E5 to E22, the second range, and then the ending parentheses. This means I want to use F5 to multiply E5 plus F6 to multiply E6 plus F7 to multiply E7 and so on and so forth. This is what we build in the objective function, right? And then we let the software to decide a minimum value for this objective. Currently, you will see 0. 0 means we haven't decided the decision variable values yet. That's why you will get 0. Next, we want to build the constraints. Let's choose J4. I want to type in constraints. These are the label too. And then in K4, I want to type in real value. In L4, I want to type in capacity. In J5, I want to type in 1. And then in J6, I want to type in 2. Next, I want to select J5 and J6. And then drag the autofill button of J6 to a cell where I can see 11 in it. I want to generate a sequence. These are actually a sequence of cities, right? City 1, City 2, City 3, and so on until the destination. City 1 is Birmingham. City 11 is Virginia Beach. And then City 2, City 3 are the mid-cities. Next, I want to build the constraint for each city. For the starting point, as I said, no matter which path we choose, the total value of the two possible paths should be -1. So let's type in -1. This is the constraint for Birmingham. For the destination, no matter from which path we reach the destination, Virginia Beach, the total value of all possible routes, all possible paths should be 1. This is the capacity for the destination. In the cities in between, the capacity should be all zeros. These are the requirements for us to make a decision, right? Next, we need to build the constraint equations for each city. In K5, I want to type in equal sign. And then I want to use a function from Excel to build this equation. It's called a SUMIF. Let's type in the function and then I will explain this function. I want to type in SUMIF and then the open parentheses. First, I want to choose a range. I want to choose from D5 to D22. And then a comma. For criteria, as you can see here, I want to choose J5. And then a comma. For the sum range, I want to choose F5 to F22. Before I close the function, I want to change D5, D22 to absolute reference, which means I want to type in $D, $5, $D, $22. For F5 and F22, I want to type in $F, $5, and then $F, $22. And then I want to type in the ending parentheses at the end. And then I want to type in a minus sign. And then I want to run the SUMIF function again. Let's type in SUMIF. And then for the first range parameter, we choose the starting city range. Obviously, we need to use absolute reference. If you are using a Windows PC, select this range and then press F4 button on your keyboard. F4 button. It will change to absolute reference. And then a comma. Here I want to click on J5 again, and then another comma. In the sum range, I want to choose the decision variables again. Also, I want to change F5 to F22 to absolute reference. And then the ending parentheses. Let's talk about these two SUMIF functions. Let's talk about the first one, SUMIF D5 to D22, this one. This means I want to look up the value in cell J5, which is value 1, in the range from D5 to D22. If I found 1 in this range D5 to D22, I want to add the value in the range F5 to F22 into the total. Now let's look at D5 to D22. Do we have a value 1? No, we don't have any. So the SUMIF value is 0, right? Let's talk about the second SUMIF, C5 to C22, this one. This means I want to look up the value in J5, which is 1, in the range C5 to C22. If I found the value 1 in this range, C5 to C22, I will add the value in F5 to F22 into the total. Do we have a 1 here? Yes, we have 2. That means I want to add the F5 and F6 into the total. But don't forget, we have a requirement for the capacity in the constraint equation. We want the total of the first constraint equation to be -1. Since the first SUMIF function is 0, 0 minus 1 equals to -1, right? In other words, the total value of the second SUMIF function in our equation should be 1. That also means the value in F5 plus the value in F6 must be 1. The software needs to decide which one is 1, which one is 0. This will be performed in the optimization analysis. This is how we build the constraint equation. Next, we can drag the autofill button of K5 to the rest of the cells in the K column. Currently, they are all zeros because we haven't performed the optimization analysis yet. Next, we can perform the analysis. We can click the Data tab on the top. And then let's click Solver. Here we need to specify objective cell, decision cells, and the constraint variables. First, in the first box, set objective. Let's choose the cell that holds the objective function, which is in cell D24, and then click Confirm. In this case, we want to minimize the travel time. So in the second option, let's choose minimize. Next, let's choose the decision variable cell range. Click the third box and then click the button next to it. Let's choose the range in light blue color. This is the decision variable range. And then click Confirm. Next, let's build the constraint. Click Add button. In the left-hand side, let's choose the constraint equation we just built. Click the button in the left-hand box, and then choose K5 to K15. These are the constraint equations we just built, right? Next, let's choose equals to. We want the value from the constraint equations to be exactly the value in the capacity column. So in the right-hand box, let's choose L5 to L15 and then click Confirm. Click OK. These are the constraints. Next, let's check the box before make unconstrained variables non-negative. Make sure this box is checked. And then in the solving method, let's choose simplex LP. And then click Solve. Now you can see solver find a solution, right? Choose Keep Solver Solution and then click OK. Now you can see all the values in the constraint equations satisfy the required value. Also, in the light blue range, we can see which path will be chosen. As you can see, from CT1, we want to choose CT2, not CT3. And then from CT2, we want to choose CT4, and so on and so forth, until we reach the destination. Also, if we travel according to the path suggested by the decision variables in the light blue area range, the total traveling time we need en route is 11.5 hours. This is how we use the network modeling technique to find the shortest path, or the path that needs the shortest amount of time for the traveler. For interested classmates, you can make other combinations of the path and then find if this is the shortest path.